So, hi everyone. So, today I will be discussing assignment 8 of this course. Okay. In the content of week 8 is related to Orgel and Tanabe Sugano diagrams. Hence, I will be discussing the problems related to these two topics. Okay. So, as usual, I will show you the two problems and waiting for your answer, and thereafter I will explain how they can be solved, right? Yeah. So these are the first two problems of this assignment. First one is related to charge transfer transition. You have to identify in this complex, that is Persian blue complex, right? You have to write down the formula, and by the formula and oxidation state you can get the basic idea what type of charge transfer transition can take place in this particular complex. Okay, so there are four options: MLCT, and metal to metal, ligand to metal, and fourth one is ligand to ligand charge transfer transitions. The second one is in octahedral crystal field, the free ion term, that is D, will split into. So here are the terms given. You have to identify which will be the right pattern of splitting for this uh, D ion term. Okay. So if you know the degeneracy of this D term, you can easily identify which will be the correct one answer. Okay. So just try to solve and revert me if you know the answer. Just type in the chat box. Okay. Thereafter I will explain. So let me write down the formula. It Persian blue. Okay. So if anybody know the answer, just type in the chat box. Okay. So this is the normal formula of this complex, that is Fe4, FeC, and 6 whole thrice. Okay. So here you can see one metal is outside the coordination sphere, which is higher in oxidation state, and one is present in the inside the coordination sphere. So basically, there is a tendency of transfer the electrons from a low oxidation state metal to high oxidation state. So typically, it show the bright color due to strong metal to metal charge transfer transitions in the visible spectrum. Okay, so Fe plus 3 ions is reduced as a result of charge transfer from the this ion. right? So this will be the right answer. And second one is simple. The degeneracy of D term is 5. Okay, so you just select here. If I calculate the degeneracy of these terms, it will be 3 plus 2, that is 5. So this will be the right answer. Okay, so the ground term energy for transition metal complexes are affected by influence of this ligand field, and you already studied that the d orbitals are split into T2Z and EZ subset for octahedral complexes. If it is the case of tetrahedral complex, the G term will be removed because it does not have a center of symmetry. Okay, so the terms will be T2 and E, right? So these are the next two problems. You have to identify the incorrect statement about Orgel diagram. Okay. Orgel diagram gives information about both high spin and low spin cases. Orgel diagram is qualitative in nature. Orgel diagram shows the symmetry state of highest spin multiplicity. And the fourth one is Orgel diagram does not show all possible terms. Okay. You have to identify the incorrect statement. Okay. I think you have studied the diagram in detail, so you can identify easily. But I'll explain also. The second one is the Oracle diagram given below is applicable for. Okay, you have to just identify that this diagram correspond to which electronic configuration, right? So if you are having a D1, D6, D9, and D3 term, you will go to the first one of Orgel diagram, first part, and other terms excluding D5, you will be going to the second part of Orgel diagram. Okay, so just try to identify. Okay, so here is the explanation. Okay, I will be discussing first the second one. So here is the Orgel diagram. This is basically the second part. Okay, so you can see here the spectra that is given in this question. Sorry, it is the it is of the left side only, right? So you can see here the ground state is A2Z, T2Z, T1Z, and T1Z. Okay, so yeah. Okay, so the appropriate configuration will be of among these. Okay, and since you are given the octahedral systems in the question itself, so basically you can easily choose this option, that is D3 D8 octahedral complex. Okay, and if I talk about the first one, the Orgel diagram is qualitative in nature. It is correct statement. It shows the symmetry state of highest spin multiplicity. But it does not show all the possible terms. Okay, and Orgel diagrams are restricted to only show weak field, that is high spin cases. That is basically, you can say, the drawback of Orgel diagram. Okay, so Tanabe Sugano diagram in it's applicable to both high spin and low spin cases. So this one is the incorrect statement, and the D option is the correct for the second one, right? So the next two, among following the necessary requirements for transition metal complex to show metal to ligand charge transfer transitions are. So here are the four conditions you have been given. First is the metal center is in low oxidation state. That means metal is having a higher electron density. It can easily transfer. Okay, the ligand should have low lying empty molecular orbitals. Low lying means low energy. Okay, the metal center is in high oxidation state. That is incorrect statement. The ligand should have low lying completely filled molecular orbitals. So here are the options A and B, A and C. Okay, C is incorrect option, so you can eliminate this one. B and D. Okay, so both B and D options cannot be the right one. Either the ligand will be in low lying molecular orbitals, or it will be uh, filled, low lying completely filled molecular orbitals. Okay, and what about this A and D? Okay, so if you are having a metal to ligand charge transfer, that means the ligand is having a element that is basically electron deficient. Okay, right? So going to the explanation, basically the CO and CN, these ligands are sigma donor pi acceptor ligand. Okay, so you have to just identify the sigma donor pi acceptor ligand, and on this basis you can say, okay, so on this basis, you can say a metal to ligand charge transfer exists. Okay, so upon the absorption of light, electrons in metal orbitals are excited to ligand antibonding orbitals. That is basically matching the level. Okay, their energy are comparable, so electron transfer is more favorable, right? So metal is in low oxidation state, and the ligand possesses low lying empty orbitals. Okay, so the A and B option will be the right answer. If they are having a filled orbitals, how can they basically donate the lone pairs? So it will be the right one. The ground state term for this complex titanium hexaqua complex. Okay, so what is the electronic configuration here? Basically, it will be D1. Okay, and just identify the multiplicity. Okay, calculate. If I fill right one electron, okay, what it will be having a spin of half. 2 multiplied by half plus 1, that is 2 spin multiplicity will be there. Okay, or if I calculate the value of plus 2 plus 1 0 minus 1 and minus 2. Okay, so if I am having L equal to 2. Okay, so what it will be? Oh, it is asking about the ground state term. You can easily identify from the orgel diagram. Okay, since it is a octahedral complex, the correct term will be, I think, this one. Okay, 2 T2Z, right? Because D orbitals are split into T2Z and EZ orbitals, right? And the next is the first excited state for a high spin D for octahedral system. Okay, since the orgel diagrams are applicable to high spin complexes, you can easily apply the orgel diagram. Okay, so if it is a high spin system, the electronic configuration will be like this. So just calculate the multiplicity, it will be 5, right? So either this will be the right answer or this will be the right answer. So since it is a octahedral system, okay, so first excited state you have to identify, so it will be 5 eg. Sorry, you have to just draw the diagram. Okay. Okay, so the first excited state for a high spin d4 octahedral system is 5 T2Z. Okay. Yeah, just see this one. Okay, so it is a d4 octahedral system. Okay, so you have to go to the first one diagram. Okay, and this one, right? Okay, the term will be reverse. In general, you see in octahedral complexes, the splitting of orbitals is taking place T2Z in lower in energy and EZ is higher in energy. Okay, but in a special electronic configuration, you see the reverse pattern. The next one, here is the Tanabe-Sugano diagram for D5 system is given. You have to identify the spin allowed system for this is a D5 system basically. Okay, so for D5 systems, the ground state is 6A1G. Okay, so this is the ground state, right? So either it can have transition from here to here and so on, but the spin multiplicity should be same. So here there are no other terms having a multiplicity of 6. Okay, so the number of spin allowed transitions, how much? Okay, so here is the explanation. Uh, yeah, so this is D5 ion. Water is a weak ligand, and according to this diagram, D5 ions in weak ligand field strength. So ground state is 6A1G. In weak field, it is 6A1G, but in a strong field ligand, it will be the 2T2Z. Okay, basically these terms you are getting on basis of electronic configuration, right? Yeah. So, since there is no sextate spin multiplicity in any excited state, so there will be no spin allowed transition. So, the right option will be none of them. Okay? Yeah. So, the next two is also related to orbital diagram. According to orbital diagram, the lowest energy transitions for this complex. So, first you have to identify the system, that is chromium plus 3. Okay. Okay, so it is chromium plus 3. And what will be the electronic configuration? It will be D3. Okay, so it is a D3 system. Okay, so just go to the orbital diagram. Yeah, so D3, since it is a octahedral system, this, yeah, so octahedral system, so it will show the spectra of this type. Okay, right? Yeah, so since here there is no high spin and low spin complex, right? You have to identify the lowest energy transition. Okay, so if I consider it as a ground state, okay, So it is yeah, D3 octahedral. Okay. Yeah, D3 octahedral will be this side. Okay. So this will be the ground state and it will be the first excited state. So this transition, that is A2 to T2, will be the lowest energy transitions, right? Since D3 octahedral is lying in this side. Okay. Yeah. So here is the explanation. Chromium is in plus 3 oxidation state. So D3 octahedral system splitting will be like this. Okay. So this transition, that is this one, will be the lowest energy transition. That is 4A2Z to 4T2Z. Yeah. So this one. You can get the idea from this values also, right? So since it is E equal to Hc bar, okay. So if there are wave numbers are given, okay, you can just put out these values here and you will be getting the corresponding values. So here you can see the wave number for first transition is the least, okay. So you will be having the lowest energy transition, okay. So hence the lowest energy transitions, this one, okay. Yeah. Okay, so to the next one is ground state term for these two complexes. First one is octahedral and the second one is tetrahedral, R respectively. Okay, so just identify the electronic configuration. It is having D7 and it is also having a D7, but there are different geometries. One is having octahedral and other is having tetrahedral geometry. So the Z term will be excluded in the second case. Okay. So just if you know the answer, revert me. Okay. So thereafter I will explain. Okay. Yeah. Okay. So let me check. Yeah, fine. So you can see both. Yeah. So both ligands are weak filled. Okay. So there will be no pairing. Okay. So if I fill the electrons, 3, 4, 5, 6, and 7. So here you can see the spin will be 3 by 2 and the spin multiplicity will be 4. Okay, so both the cases the spin multiplicity will be 4, right? So since it is a D7 system, okay, so just so this will be the incorrect one. Okay, select among these. Okay, so here is the orbital diagram. Okay, so the ground state uh, for D7 octahedral system, right? You will refer to the right part. Okay, and for the tetrahedral system, you will be referring to the left part. Okay, so here in case of octahedral complexes of D7 system, this will be the ground state, that is 4T1G, and in the case of tetrahedral, that will be 4A2. So 4T1G and 4A2. Yeah. So this one will be the right answer. So moving to the next two, what is the ground state term for D2 configuration? Okay. So just basically these are the term symbol, or you can say just fill the electrons like this. Here is the momentum values. Okay. So what will be the spin multiplicity? It will be 3, right? And if you calculate the value of L, that will be 2 plus 1, that is 3. If I write out SPDF, 3. So 3F, you can say the ground state term. Okay. And what about the second one? The term F. Same goes here. You know that degeneracy is 7. Just identify. So here is 5. Here is 9, and triplet 3, 6, and 7. Okay, and here is also 7, right? So what will be the right answer? You know, the F term is split into T1Z plus T2Z plus A2Z. Okay, so this will be the right one. Here A1Z will not be the right. Okay, you can just refer to the diagrams also. Okay, so orbital diagrams gives information about weak field, strong field, complex, both weak and strong. Okay, and none of them, because orbital diagrams gives information about high spin complexes. So the first one, that is weak field complex, will be the right answer. And the second one, how many microstates are possible for D2 configuration? Okay, just apply the formula, that is NCX combination formula. Okay, X is the number of electrons that is present here. Okay, and the value of N will be the maximum electrons that can be filled out in that particular orbital, or you can say uh, from this formula you can also get the value of N. Okay, so just do it by your own and tell me the answer. I will wait for 2 minutes. Okay, so you can calculate the value of n in two ways. Okay, you are having a d orbital. Okay, so how many electrons can be filled up? Maximum, maximum 10 electrons, right? Because there are five orbitals. And if you just put the value of d, that is that is 2. Okay, so it will be, that will be 10. Okay, and just apply the formula, that is 10c2. So factorial 2, this one, 10, 9, and 8, and so it will be 45, right? So you can calculate the microstates in this way if you are if you have been given the electronic configuration, right? Or if you are given the energy term, you can easily apply the formula 2s plus 1 multiplied by 2l plus 1. Okay, I think I have discussed this type of question in the uh, last session. Okay, yeah, see, in the last session I have there was a question that was related to metal to ligand charge transfer. I have explained in the right way, but I have chosen the incorrect answer, so you can correct it. I have also corrected in the PDF of these slides that you are getting, right? So which couple is absent in Orgel diagram, right? So basically, there is a formula to calculate Orgel diagram, right? So if you are having dn and dn plus 5 term, you will be getting the same spectra, right? Or if you are having this one, right? So d10 minus n will be having same spectra but in different environment. Okay, so if I talk about d1 and d6 in octahedral, they will be showing this spectra, and also that is d3 and D9 octahedral, and they in tetrahedral. Okay, so both having the same spectra in the Orgel diagram. Okay, so using this simple formula, just apply here D1, D6, and you can calculate the gap. It is 5. Here is also 5. Here is 4. Here is also 5. So this couple is absent in Orgel diagram. Okay, so the next one, how many transitions are expected for this chromium plus 3 on the absorption spectra? So basically, it is a D3 system. Okay, so just use the diagram and calculate how many transitions are possible. Okay, since here the environment, that is octahedral or tetrahedral, is not mentioned, and there is no weak field or strong field ligand, so you can just refer to D3. Okay, so whether it will be in tetrahedral or octahedral environment, it will be having three transitions. So one is here, one is here, and one is here. And similarly, if it is in tetrahedral environment, it is one, two, and three. Okay, in both the cases, it will be having three electronic transitions. Okay, so it will be showing three peaks in the absorption spectra. Okay, understood? Okay, so moving to the next two. Non crossover region, it seems in between. These are the terms given. You have to identify the crossover region. Okay, and in the second one, the ground state term for this complex, that is a uh, D8 complex. Okay, so just since water is a weak ligand, fill out the electrons. Spin multiplicity is, sorry, spin is 1 and spin multiplicity will be 3. Okay, so same way go to the D8 system, D8 octahedral system, and since it is a high spin complex, since water is a weak ligand, you can just refer to Orgel diagram. Okay, so I'm moving there. So D8 octahedral. Okay, so D8 octahedral will be lying on this side. Okay, so the multiplicity is 3, and what will be the ground state? That is A2. Okay, so 3A2Z will be the right answer for this one. Okay, just what is the summary of this basically the session? You have to remind the Orgel diagram, and all these problems will be solved easily. Okay, the first one, you have to identify the non crossover region. Okay, where basically two spectra are not bisecting each other. Okay, so yeah, you can see this T1, T2, right? So T1 and T2, they are not intersecting or not bisecting this T1, right? Okay. So T1F and T2ZF, A2ZF, T1GP, okay, and both are F, or T1GF and T1GP, okay. So A to Z, I think, is bisecting. Just you have to observe non-crossover region. Okay, they are, if these two terms are not crossing each other, so there will be the crossover region. Okay, so just sketch this diagram if you remembered it, and just identify and tell me. So it will be T1GF and T1GP. Okay, so T1G and T2Z, they are both bisecting each other, right? So this will be the right answer. Okay, so this was all about this session. Okay, so if you have any query related to any assignment, you can just post to the discussion forum, and I will be get back to you there. Okay, so thank you very much for attending, and if you have any question, just simply post into the discussion forum, right? So I am ending the session now. Thank you very much.